welcome. In this session, we're going to state the Lagrange multiplier theorem. We won't prove it, and we'll summarize the results for this lecture. The Lagrange multiplier theorem is a very powerful theorem for multivariate calculus. You can look these up. My favorite solution involves some ideas from differential geometry that include things such as a tangent space, but there are lots and lots of proofs available for this theorem. So the theorem states that if you have what we're calling a nice objective function, so if it's an analytic function, if its Taylor series converges everywhere, and you also have a nice property function, so you can differentiate them as you need to, that suppose that you have a point that's a local minimizer or a local maximizer of this constrained problem. Well, when you have at such a point, so this might not be unique, there might be many of them. There might in fact be a family of them. They don't even have to be just a finite number of them. But at every stationary point that's either a local minimizer or a local maximizer, what you have is there is some scalar multiple that transforms the gradient of one to be the gradient of another. So this is the Lagrange multiplier theorem. And what we did in the previous sessions was we built up an intuition that perhaps this was true, and then we can either prove it ourselves or we can go searching for a proof, and we find that indeed this is a very powerful result. And we're going to use this result frequently in the rest of the course. So now there's another way that we could be visualizing all of these. Let's go back to our problem where we had a squared vector norm objective function and a linear constraint. Well, we could represent that squared vector norm because the underlying vector space is 2D and the levels are a scalar value. We could represent those in 3D. And if we did, we would find that it's a right circular paraboloid, a surface of revolution. And then that line would be, the constraint line would be a locus in that W1, W2 plane of the points that satisfy that property. And if we then extend that and say, well, it's got any of these levels, that as we shoot up, what we find is that this constraint surface and this objective surface will intersect, and they'll intersect exactly at that level, and we could try solving this problem geometrically as well as algebraically. So what would our second problem look like? Well, in that case, we have a tilted squished ellipse, and then that'll be an a rotated elliptic paraboloid. And then our constraint function in the plane was a parabola. And if we extend that upwards infinitely, we see that this intersection of the constraint ellipsoid and this paraboloid of one sheet is again a locus, and again it has a minimum, and we could try geometrically to find that minimum. And what we can observe is that in both of these cases, we're going to get these gradients that are parallel. And then if we take a look at our third problem, where it was a linear objective function, that amounts to being a tilted plane. And so we have a tilted plane, and we have our paraboloid of one sheet, and these will also have an intersection, and that intersection point where it's a minimum level, that's going to be the solution to our constraint optimization problem. So this only works, these visualizations only work in 2 dimensions, but in 2 dimensions, they seem to be pretty powerful, don't they? So let's summarize our lecture. What we found is the minimizer is in a level curve of the objective function. The minimizer is also in a level curve of the property function. At the intersection point, these gradients are parallel. They don't have the same magnitude, but they have the same direction given this possibility of plus minus, so they might be flipped oppositely, but that still is parallel geometrically. And there is a number, and we'll use mu for multiplier to refer to this Lagrange multiplier, that transform one of these gradients to the other gradient.